Okay, so you remember last time we talked about an action potential and how that propagates along the cell, right?
Right.
So normally we have the resting potential, we have negative on the inside of the cell and positive on the outside.
Right.
And this is kind of what we're looking at the cell, right? But sometimes they graph this to kind of explain electrically what the action potential looks like. So they'll have like an axis like this, right? And we'll say, just gonna make sure, so yeah, we'll start at negative 70. So this is not necessarily a perfect x coordinate,
Right.
but we'll, yeah. Okay, so for our purposes, so then this is about 20. Okay, so resting membrane potential on the inside of the cell is around 70 millivolts. Yeah, that's just kind of...
So that's the resting charge on the inside.
Yeah, on the inside of the cell. And then when you have cell stimulation, it starts changing that potential, right? So, so the stimulus is what's going to cause this change in charge, right? And there's a point called a threshold, right? And when the stimulus gets to a threshold point, the voltage gated channels would then start to open, and then we'd get like a spike like this, and then it would come down like this, and kind of level out, okay? So right here, this phase is the depolarization. This is when this is switching, right? Sodium-potassium channel, so sodium is coming in the cell, right? Switching the charge. And then we have a period of repolarization, which is when sodium or potassium gated channels open up, let potassium out of the cell to bring the charge back down.
Right.
Right. Okay. And the graded potential is like right here. Okay. This is where the stimulus is starting the action potential, basically. And depending on the strength of the stimulus gives you the strength in the grade of the graded potential, right? So if this graded potential doesn't meet threshold, it'll just kind of go like this and flatten out, right? It won't initiate an action potential per se, because you wouldn't get to that voltage which opens the sodium channels. All right? So let's see here. But let's see. So there's proportional to the stimulus strength. So graded potentials are proportional to the stimulus strength. A weak stimulus applied briefly causes a small depolarization, which quickly returns to rest. Progressively stronger stimuli result in larger depolarizations. A stimulus applied to a cell causes a small depolarization. Let's stick with it. Disappears because it's like. Okay. Cool. So, and this kind of brings up summation and stuff like that. But let's see. That changed. So. Okay, so the thing that causes a graded potential is a stimulus to a cell, and that's kind of a vague term, but it's basically when a cell is stimulated, the permeability of that cell changes, and so it's letting sodium out and stuff.
Right. So what's stimulating the cells?
Like it could be anything. It could be electrical impulse. It could be you touching, like when you touch things, that's stimulus to cells in your hand and nerves in your hand that affect the permeability of your nerve cells and things like that. So it could basically be anything that causes some imbalance of this, because there's a ton of sodium on the inside of the cell, right?
Right.
And concentrations always want to go from high to low. So whenever sodium gets a chance, it's going to push out of the cell.
Right.
And so if you disturb the cell at all, you're going to affect the permeability, because it's kind of like like a time bomb type of thing, right?
Right.
Depending on how much you stimulate that cell determines how much permeability you'd get. Okay. It talks about summation a little bit.
Yeah, I have temporal summation and spatial summation.
Okay.
I don't even know.
The difference between those two. Let's see. Okay. What does your thing say? Let's see. Temporal summation, just one.
And spatial is multiple axons coming to multiple dendrites.
Oh, okay. Okay, spatial summation, multiple axons coming into multiple dendrites. Oh, okay. So I kind of was talking about this. So a spatial summation would kind of look like this. So you'd get a graded, so there's only one axon dendrite interaction
Right.
with temporal, right? Is that what you said, just one on
Yeah.
temporal? Okay, so you get something like this. So you get a stimulus, and then it would go away. Stimulus, it would go away. Stimulus, it would go away. Okay, but with a spatial, because you have multiple axons connecting to multiple dendrites, it would kind of look like this, because this is like time in between this ending of the impulse. But if you have multiple ones, you'll get one doing this, and then another one will hit, and another one will hit, kind of like that. And so every time a individual axon, right, sends that signal or stimulus, it has an additive effect on that permeability. Does that make sense?
Yeah.
And so this is more likely to hit threshold, right?
Right.
Either this one has to send a stronger stimulus or has to recruit more axons. Kind of make sense?
Yeah.
So spatial, you got multiple stimuli, so they kind of add to each other. And so this would kind of look like this, right? And then it would hit threshold, and then the voltage gated channels would open, right?
Right.
And so, let's see, so, just look here, so. Okay, yeah, progressive stronger. Yeah. That's my best shot at that. I don't really, let's see, what else does it say?
Well, the graded potentials, it talks about IPSP inhibitory.
Okay. IPSP, inhibitory, excitatory. Okay. So, basically, that's talking about the direction of this graded potential.
Right.
If you want to stimulate something, you want to depolarize, right? And so, because you're getting it closer to threshold. So that's a stimulatory effect. But the opposite, inhibitory, would be hyperpolarization, so you're bringing it lower. Does that make sense?
Yeah.
So you're taking it further away from threshold to keep it from being stimulated, right?
Right.
And I don't know, that's pretty much